Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
It may seem a little bit odd that the title of this video is Conservation of Angular Momentum, even though we haven't defined angular momentum itself yet. But in fact, these two topics can be wrapped up quite nicely into one presentation, and that's what I'm doing here. So we have this table here that needs to be filled up. So we know that in linear motion we have momentum p, and it's a vector quantity. And if we want to change the velocity or momentum of a particle, we know that we need a force F, like this. And why I have force written as it is because the angular version of force is not quite a force, but we call it torque, tau. To produce angular movement or motion, we need torque on that object to make it rotate. And this is what we know so far. And how did we get torque? What we did, in fact, was that we had the linear version of it, F, and then we took a cross product with the position vector R, like this. In fact, we can do the same thing in the momentum realm. So for angular momentum, first of all, we have the linear momentum, and we take, in the same fashion, cross product with the location vector R. If this is a particle, then it's from the pivot point of the particle. If it's a larger object, then it's just from the pivot point to any given point on the object. But what we have as a result is a quantity called angular momentum, denoted by L, and it's also a vector quantity. Let's study the simplest case first. That is, we have a particle at some location R moving at velocity v in that direction. According to what we have for angular momentum, so let's write it another way. So L is R cross P, and we know that P is also m times v, like this. So we could go on and just take a cross product of R with the v and multiply it by the mass, and hence we would have the angular momentum for this particle. Even though it's not going in, or it's not even rotating about this point, it still has angular momentum, even though it's going on a straight line. So this is how you calculate the angular momentum for a particle. And if we want to do it for any given object, we have to sum all these individual angular momenta of that object. We're not going into details, and the calculation of angular momentum in general case for a rotating object can get pretty tricky, but we state the following result. If the object is symmetric about the rotation axis, in that case the angular momentum, or the summation of the individual angular momenta of all the particles, results into the following result. The angular momentum of the object is the moment of inertia multiplied by its angular velocity. This result is true, as I mentioned, only if the body is symmetric about axis of rotation. And cannot be generalized to all objects. That is important to remember. So what are the objects that are symmetric about axis of rotation? So anything that is round, so like flat disks or gears, a dumbbell is one that comes to my mind right off the bat. So in general, the applicability of this formula is it's somewhat restricted, but it has the nice property that the angular momentum is in the same direction as the angular velocity. We can also see it from this figure for rotating gear. So when we curl our right-hand fingers to the direction of the rotation, the thumb will point into the direction of the angular velocity and the angular momentum. This is not the case for unsymmetric object. In that case, the L vector might be pointing somewhere off the axis of rotation, and the L vector itself can be rotating about the axis, so the situation gets much more complicated. So only accept this result for the simple case of symmetric objects. Now let's go back a little and work on the fundamental definition of angular momentum. So this is a cross product of r and v vectors, so we can write it in the following form. So r times v times sine of the angle between the two. And if you look at the case of this particle that we had, so there we have angle phi. Then we also have the angle phi here, like this. And r times sine phi is then this perpendicular distance. And what happens now when the particle speeds away? What happens to the angular momentum? So in this case, we can imagine that the new location is somewhere here. So that's going to be the new r vector. Let's call it r2, and it has still the same velocity vector, v. Let's make it straight if possible. Okay, no luck this time. Once more. There we go. And we notice that the perpendicular distance, which is r sine phi, that stays constant no matter how far the particle is from the so-called pivot point O. So because mass is constant, r is constant, or no, r is not constant, but r times sine phi is constant, and v is constant. So in fact, the magnitude of the angular momentum here doesn't change. So it looks like, at least in this special case, the angular momentum is conserved if we don't do anything for the particle. Okay, so we have the rest of the table to fill out. So what is the change of momentum in the linear world? So change of momentum, we mean as a function of time. This is Newton's a second law that says that one requires a force to do that. So let's do this little exercise. So we have, in the same manner as we filled up the rest of it, or the first part of the table, so we have something changes with time equals something else. So in the linear case we had force here, so we have force here. Angular case we have momentum, so torque. And what else? In the linear case we have P, so in the angular case we are going to have L. So although this might look a bit of a hand waving with what it is also, in my opinion, a nice demonstration of the symmetry in physics that in a lot of cases is present. So the linear and the angular realm are pretty similar to each other in terms of formulation that we have seen. But this result here now says that if we want to change the angular momentum L, we need torque. Just like if we want to change the momentum of a linear particle, we need force. And that resulted into the principle of conservation of linear momentum. So from this result, we can state the principle of conservation of angular momentum. So the change in angular momentum as a function of time is 0 if no net torque acts on the object. Like this. A classic example of this is when a person is rotating initially with arms extended, and then when he pulls them in, the angular velocity increases significantly. And we can show this quite easily because the person here is symmetric about the rotation axis that runs through him like this. So he has at any given time angular momentum which is product of the moment of inertia and angular velocity. And this product now stays constant, so I1 omega 1 is same as I2 omega 2, and we can solve for omega 2 to be omega 1 times I1 divided by I2. And I2, the moment of inertia in the second case, is smaller than in the beginning because the mass is closer to the rotational axis, which means that the angular velocity must increase in order to conserve angular momentum.